What does that mean in terms of spontaneous? Delta G is negative. There's a correlation.
Yeah.
But why is delta G negative? Let's go, because that's also still part of what we... It's what?
Spontaneous.
It's spontaneous, but why is it negative? What was the basic premise to what spontaneity was?
Oh, the amount of randomness that it's producing?
Entropy?
Entropy?
Yeah.
The change in entropy, what type of entropy? Of the universe, absolutely. And that when that is negative, then it's spontaneous. Is that what it was, right?
Right.
And then that was equal to delta S of the system plus delta S of the surroundings. We correlated, it's hard to figure out what the delta S of the surroundings was, so what did we do with that? We figured out delta H of the system in relationship to delta S of the surroundings, and now we had an equation that gave us Gibbs free energy that dealt with delta H, enthalpy of the system, with delta S of the system. And that we could figure those things out, and as a relationship to that we figured out delta G. Delta G was negative T delta S of the universe, which is why when delta G is negative, it is spontaneous. That's where that correlation came from. Just to recall where we're at. Delta G, how is now, what else, what term, what is the actual name of delta G? Literally the definition. Gives us free energy, which means that that was all what? The maximum work that's available, possible, right? To do work, free energy, okay? And we never fully defined what E was, right? So I'm going to define it in that context, work maximum available, and then I could correlate it to delta G. Was there a correlation to K with delta G?
It's under non-standard conditions.
Under non-standard conditions, what did we do with it? Delta G equals delta G under standard conditions plus or minus RT times the log of K. Right? So we did have a correlation between those. And when I'm at equilibrium, which is what K is, then that equation is equal to 0, which means that delta G under standard state conditions is equal to what? Negative RT log K. And there's your delta G under standard state conditions, this one, in a relationship with K. If I could correlate these two, then I could substitute that and correlate those two as well. And that's all I'm going to do to start. Okay? Okay. With that being said, let's get into it. What do I have here? Just another review. Spontaneous versus non-spontaneous. Redox reactions, delta G is negative for spontaneous, it's positive. There, the cell is positive for spontaneous and negative for non-spontaneous, and K is greater than 1 for spontaneous and less than 1 for a non-spontaneous. Those three things we know for each of the conditions of spontaneity and non-spontaneity conditions. Okay? Just to recall. Now let's put them together. So let's define really what E is. And E is given as the potential energy difference in joules per charge in Coulomb. Okay? And that just relates to a charge like an electron, a proton, whatever else. I'm going to simplify this even more. I'm going to call potential energy maximum work. That's the potential energy I have. And maximum work was what? Delta G. Does that make sense? So then it's just this term here that becomes challenging in how do I assess what a charge is, right? Okay. So in doing that, I could simply, if I take this and I move the charge up here, I get the charge times E equals the maximum work. And that's all I did here. But I added one thing there. What did I add?
Negative.
The negative. Why? So the system is doing work on something. That makes it what? A negative. Yes, yes. Right? So that's where the negative comes in. So I have the maximum work is equal to negative this charge thing that I might not know what to do with just yet, and E of the cell under standard conditions. And we already know what I'm going to correlate this to. This is delta G. So I have something delta G related to E. However, I still got that Q thing there. Like, what is that? How do I figure that out, right? How do I simplify that? And what I can tell you is that I'm going to throw in this Faraday's constant, which is F equals to 96,485 coulombs divided by 1 mole of electrons. So if I move this up here, and I say n in relationship to the number of electrons being transferred, and I multiply it by this number, I now have what I call Q. Okay, so let's take a look at that. So Q equals n times F. N is just the number of electrons being transferred. F is a constant, 96,000, that number, that's all F is. So if I plug NF for Q into our equation with work max, I get negative NFE of the cell under standard state conditions. This is given as the Faraday's constant. This is, can we solve for that out of curiosity?
Solve for one?
The E under standard state? Yeah, absolutely. That's what we did all Tuesday, right? Okay, no big deal if I have a chart or I'm given the numbers. And then can I figure out this? If I call the number of electrons.
Yes, because it's.
I look at what? I look at the redox rate, I look at the half reactions, and I can see when I balance them out how many electrons were transferred. So now I can actually solve for work max in relationship to E of the cell under standard state conditions. And what's work max? That's delta G. There's my correlation between E of the cell and delta G. And what I'll do there is just this, and there, this is the E of the cell. There's my delta G under standard state conditions. This is just the number of electrons being transferred in the overall cell equation, which you can get from the half reactions as well, right? Once you balance it out according to the electrons. This is always given. That number never changes. And this is, you can solve for, the standard cell potential. Okay, so there's my correlation. So obviously we want to use that in some capacity. Okay.
On these? On a table, I just don't want to leave it.
Yeah, I actually suggested somebody brought him in, and I
Okay.
suggested leaving
Yeah,
him because that's
okay.
probably
Like where the necklace is? Okay.
that's probably where they go back. I don't know about you guys, but me, I've left keys before, and I always go right back to the spot when they're not there. Then I don't know what to do. When they're there, I just pick them up. Usually, nobody else takes them unless they're putting them somewhere where you wouldn't know.
Leave a note.
So yeah, or leave a note, which then that can just go away. So I usually tend to leave it. If it has money or something in it, then I'll maybe bring it somewhere safer for them. But, okay, so now let's take a look at equilibrium constant with E cell potential. So I have this equation here, the correlation between delta G standard state conditions and E of the cell under standard state conditions. And we did this, which, remember, I just walked you through this a minute ago, right before we started. Delta G standard state conditions is equal to negative RT log K. And there's my correlation between delta G under standard state conditions and the equilibrium constant. So I can obviously take this and just plug it right in there, and I now have my correlation between E of the cell and K. Right, so I just take this is equal, I plug that in here, and I get this. No big deal. Once again, you don't have to rederive these things. I'm just showing you where they're all coming from, so it makes sense based on knowledge you already have. Right? You're just going to have to solve for it. But if I want to solve for this, I got to have this on a side by itself. So I'm going to divide both sides by NF. And whoops. Okay, maybe I should do it over here. So I have NF E of the cell, standard state. I'm not going to. When you see this note here, that just means standard state, so I don't have to keep saying it over and over. All right. Because we are going to get into non-standard state conditions, and then you won't have this up there. This is just representing that, just to clarify. And this is RT log K. Okay. So all I'm going to do here now is I'm going to divide both sides by NF, so those cancel, and now I have this here. Everybody okay with that? Pretty simple manipulation, no big deal here. So if I do this, now I'm just putting E of the cell by itself on one side. Okay. Now, this is a constant. What is this one? 8.314?
Yeah.
This is a constant. What was it? 96,485? Is this a constant? The T?
No, unless it's at standard. Oh, it's at standard.
It's at standard state, so what is it?
So 273?
25
Oh,
degrees Celsius, it's standard, right?
all right.
So it's 298,
Yeah.
Okay.
right? Okay, so that means that I have all of this is basically a constant, right? And I should put, no, I'm okay there. Oh, one thing I should point out just for you guys. So you see, and we discussed why this was negative, right, when we got to this point. But then when I do this and I put this down here, because this is also negative, the negative and negative go away, so I have positive and positive. This is a real subtle thing. I just want to make sure that's clear, so you don't get caught up with that. So that's why there's no negative here. So if I can figure out a term for this group here, then that's just a constant. And let's call that J for now. Okay. So now I could say E of the cell is equal to J, move the J up here, over N log K. Then if I take J, remember that's just a constant, I'm going to write that up to make sure that's clear. I don't want to use K because you have it up here in your equilibrium constant. And now if I take this and I multiply this by 2.303 or something like that, I think it is, then what does that do? That converts the natural log into the log to the base 10. So I multiply this number by this. I now have a new constant, which I'll call Z, let's say, over N log K. And the log is now different. And that's all you really have here. And this number comes out to be 0.0592. Which what I'm saying is Z is 0.0592. That's just the number for the constant that I called Z over here. And that's just the collection of multiplying 8.34 times 298 divided by 96,480 whatever, 85 or whatever it is.
That's the 2 point?
And then multiply by 2.303. And that gives you 0.0592. And that's just a constant. Okay? So what did I do? I just made this, and see there's your 25 degrees. I just made it easy to get the correlation between E of the cell and log K, or K, with the log in front of it. So what I'm doing there basically is all I need to solve for, if I want to solve for K, and I have the information to solve for this, I put in the number of electrons transferred, I put in E of the cell, and I can solve for K. If I want to solve for E of the cell and I have K, and I know the number of electrons, I plug those in and I can get E of the cell. That's my correlation, and that's given right here. So that's what this number is, that's what this is. Here's the first one I gave you didn't have these fill-ins. Now we just walk through, this is the fill-in between delta G and E of the cell. Here's the fill-in between delta G and K, and here's the fill-in between E of the cell and K. And so this is a more complete picture of what we saw in the first slide that illustrates the going in between each one of these components in order to get another one. And you don't have to know everything that we just did to get these. I only presented it so you had a sense of where they were coming from based on your previous knowledge. What you need to know is these. So if I have this and this, or if I have this and I can get these, can I take these and turn that into my delta G or whatever else? You need to know these three things and how they correlate and interchange between the different parameters of electropotential and thermodynamics. Is that okay? Okay. One thing I also want to point out here, this is log, this is natural log, two different logs. And that's generally how they're seen in the textbook. So don't get confused by that. Make sure you hit the right button on your calculator, because that's all you really have to do, right? So just make sure you hit the right one depending on what you're trying to solve for. Okay. What do we have here? Some backwards way of putting them up. Okay. So here, I have the electrode potential here. Let's calculate delta G for this reaction. So I have this information here. Let's go back to delta. I want to figure out delta G. I know this. Do I know this from that? No. I maybe can figure that out, but I know I could figure this out and I can go directly to here, so I probably want to use this, right?
Gotcha.
And this is exactly how you're going to assess it. So if I do that, I look at this and I say I2's on the right side there, right? So it's being reduced. BR is being what? oxidized, going from -1 to 0. So, and this is the right direction, so I just simply add those together. I don't have to reverse anything. And I quickly identify that it's going to be a negative number, which means it's non-spontaneous, right? And it's just this and this, so what's that? Something like 0.55 negative? Is that what that is? Negative 0.55. What else do I need for that equation?
You're going to need the n or the number.
Number of electrons. How many electrons are being transferred here?
2.
2. So then I go back here and I say, okay, I went negative 0.55, so negative is a positive now. I have 2, I have Faraday's constant, I put all that together and I get my delta G. The only thing that I didn't tell you, because I don't want to get you mired at this point in the semester, I don't want you to get too locked down in units. It should come out in joules. Okay, when you use this equation and you use the numbers we just talked about, this should come out in joules. Okay. You can look up if you want. This is you know, the Faraday's constants in coulombs and how coulombs multiplied by volts from the E cell end up in joules, but they do. And if that number is really big, you can convert it to kilojoules to make it look a little simpler.
For Faraday's constant, can we use 96,500?
That's what you use. That's exactly what you use. No, nothing else to use but that. That's always for the F. So that would apply here. It would apply just here in these three. It's going to apply again a little bit later for non-standard conditions. But for these correlations under standard state conditions, that's the only Faraday's constant you're going to use. Okay? So then whatever that number is, that would be the answer to this question. Not too bad. Okay. Okay. So now it's saying the next example here, I guess they're not giving us the rest of the other one, but that's just plug and chug at that point. Calculate the equilibrium constant for the following reaction from the standard electrode potential. So I must have that. Wait, what is let me see, is that different? Yeah, it's different from here. So here I'd have to give you a chart. Whoops. Or do I?
Oh, you skip the.
So I want to calculate the equilibrium constant. I need to know this in order to get the K. So I need to have a chart to figure out what that is, right? From the chart, then what's that chart? If I give you, so the last one I just gave the way, the direction it was, what if I gave you a chart? What are the electrode potentials? What's another way to call that? The reduction potentials, right? And that was important because in the chart itself, you're only seeing the reduced direction of the reaction. So that means you have to determine here, F is 0, Fe is 0, 2 plus, was that oxidized or reduced? Oxidized, it lost 2 electrons. So if that was oxidized, then whatever I saw on the chart, I'd have to flip the sign. Then the SN4 plus to SN2 plus clearly gained 2, so it was reduced. So whatever I see from SN4 plus to SN2 plus, then that's whatever that electrode potential is for that reaction, because it's already the reduction half. Just to remind you what you do when you look at those charts, right? That's what we talked about on Tuesday. Does that sound familiar? Guys? Okay. So then, with the chart, I figure out what the E of the cell is. What's my N here? And what is it here? 2. I went from Fe, this is balanced, right? So I went from Fe to Fe2 plus, what did I do? Lost 2 electrons, and I went from 4 plus to 2 plus, I what? Gained 2 electrons. 2 electrons were transferred, 2 goes for the N, 2 electrons. So I have this, I solve this from some chart, and then I solve for K.
Do you look at
Okay.
both reactions for the electrons transferred, or just the one being? Does it have the balance?
Anybody want to answer? No, that's okay.
Well, you just want to see.
Right? In the half reactions, each one is going one way and another, but overall, only 2. 2 are coming off one thing and going to another thing, and that's what creates the half.
Right. You can use 45.
Okay, so that should,
Equal.
do we solve here? No, there are 2 electrons transferred. They tell us a little more in this problem. Oh, here, okay, so here they're putting this, so I have FEs on this side, I have the SN4 plus, so this is already set up. By the way, everybody knows when I'm doing that, when I give this, I'm saying FE's on this side already, Fe2 plus is on that side. That means that that's the electrode potential for that half reaction.
Right.
Right? In this case, this is being oxidized. So in the chart, this would be flipped, and this would be a
Negative.
negative.
Right.
Just to recall what we went over Tuesday. I think that's got to be really, really clear when you're looking at a chart versus when I'm just giving you this, right? That's why I told you forget about the method in the book, only do the method I'm talking about, because it makes it a lot easier. Flipping.
I know I asked this last class, but I don't remember. If you have a coefficient in front of the.
Nope, not in this, you don't worry about
It
it.
doesn't affect that.
But we are going to worry about it when we get to the non-standard conditions, because why? Where would we worry about that? In the three things we're looking at right now, E of the potential, which we showed before, that did not play a role. Delta G, does that play a role? No. K doesn't play a role.
Yes.
Yes. How does it play a role with K? How do we solve for K?
Oh, the equilibrium.
It's
Products over reactants, and how do we set those conditions?
Oh, and then it comes squared.
Yes, yes, so it will play a role when we get to K.
Okay.
Okay, but that's under non-standard conditions, because under standard conditions, it could be under standard conditions as well, but usually you're not gonna worry about it as much.
If the, like, you know how before in the beginning of the chapter we were balancing half reactions so that we could balance the whole entire reaction?
Mhm.
If it wasn't balanced, we would have to balance the whole thing, and then that's when we'd have to take.
It depends on what you're trying to accomplish. Here, why would you have to do that?
Here you wouldn't have to do it because you have an equal number of electrons.
Because you need the electrons. Absolutely. So if you didn't worry about the electrons in any particular thing, then no. If you cared about K, yes. It all depends on what you're solving for, what you're looking for. Absolutely. If you're just looking for the electrode potential, no. Doesn't really matter. Okay. So, they're going to tell, okay, so then what did we do here? Okay, so this is already given in the proper direction, so this is going to be 0.60, right? Because everything's in the proper direction according to the equation. 0.6, by the way, if it's 0.60, then is that spontaneous or non-spontaneous?
Non-spontaneous.
Spontaneous.
Spontaneous. Why is it spontaneous?
Oh.
Because E is positive. Yeah, see, that's why you missed Tuesday. And that's what we look. Everybody on this side that was there, they knew right away. And in doing that, make sure you look at the notes in the second half if you did miss Tuesday, because how I did this is different than how the book does it. Right? The book says something about E of the, what's the final, the anode or the cathode? The anode, so it goes E anode minus E cathode or something like that, right? The electron flow goes from the cathode to the anode, right? So it'd be, and they do something like that, where it's just a memorize. Here, if you understand how to deal with the tables, and you know that the reduction potentials, you figure out which one's oxidized, reduced, you flip the one oxidized, that you just flip the sign and just add them together.
Right.
And I like that method. I think that's a cleaner method in solving this. Okay, so I get 0.60 volts here. Okay. And that's illustrated here. By the way, what are they doing here? Basically the book method. That's why they have the plus and the plus there. That's from a minus and a minus, which I told you don't worry about. Don't do that. Just add them together if you get them the right direction. And there's the 2. So I put this times 2. I divide by 0.0592. I take the inverse of the log, and I get 1.8 times 10 to the 20K. Now, from a practical perspective, what does that really mean to this reaction, this one here?
The equilibrium is very low.
It's favoring the product a lot, right? Does that make sense to what a voltaic cell is? And the idea of spontaneity, absolutely. That kind of wraps up all the things we've talked about, right? We've talked about spontaneity. This is positive, so it's the E of the cell is positive, so it's spontaneous. The K indicates that that's the direction it wants to go, right? Because you have the products over the reactants. So a high K, where did we see a high K before? K of formation, right? Really strongly drove that way. Where did we see a very low K? KSP, right? So that was where it didn't, very few of those things turned out into ions. So here you could see that correlation, that this is a really strong K, which means it's really favoring the product, which makes a lot of sense since it's a spontaneous reaction. And I put together 2 half reactions that should flow without any input of energy to create that energy. Right? That kind of wraps up all the things and the discussions and where we get to at this point, hopefully. So that's what this is telling you. So in other words, you guys can assess these things and kind of correlate these things together at some level and have a sense of what it all means and why. So if you look at a K, K shouldn't just be K. K is like, okay, that just means I'm favoring the products a lot here. And then what else would go along with that based on the K? So if I flip that equation, what would the K be? Really, really low, right? Because it would favor the reactants and it wouldn't want to go this direction. There'd still be an equilibrium at some point, but it wouldn't be favored going this way. And where did we see that? So let's say I have, let's say non-spontaneous. So if I put in energy, I could force it that way. And by the way, if this is the electropotential of this cell, and I wanted to reverse this, how much energy must I put into, at least how much energy must I put in to reverse that? I have to put that amount of output to get it going back the other way, right?
Because it's the.
Yes, right? And I have to put a little more in to drive it the opposite direction. That's what the E is indicating as well, in terms of how to motivate. So then if these are voltaic cells, what was the other type of cell?
Oh, the electrolytic?
Electrolytic. And what did that mean? I had to drive with energy going the other way. So how much energy would I need in an electrolytic cell to force this the opposite direction?
0.6.
More than 0.60. Just to kind of give you a sense of all of this and how it all fits together. Hopefully that kind of gives you a good sense of what's happening here. Okay. Now, as before, when we talk about the standard state conditions, that's because it's a nice way to compare things across a plethora of different ideas, whether it's delta G, delta H, we talked about, delta S, E under standard state, so of course there's going to be E under non-standard state conditions. And by the way, if I take something out of its standard conditions, whatever, any of those things that I just described, right, any of the thermodynamic characteristics, or E or whatever else, does that mean that I've now, let's say I have something under standard state conditions and it's spontaneous. Does that mean if I take it out of standard state conditions, it's now going to not be spontaneous? Not necessarily.
Depends.
It could be even more spontaneous, or it could be less spontaneous, or it could be now non-spontaneous, or inversely, right? You don't know what those non-standard state conditions, how that will change the effect of what you have. So we looked at non-standard state conditions for delta G, and what were they? Delta G is equal to delta G under standard state conditions plus RT times ln Q.
Or K.
ln Q, which Q could be K, absolutely, right? But if it was K, then that means that the delta G would be 0, the new non-standard state conditions, right? So, okay, perfect. That's exactly what we're going to look at. So, clean up here, taking me out of what I think is the way. Okay, they're saying that here, by the way, what are standard state conditions? For concentration. 1 molar? So you're looking up here and you see zinc plus copper 2 plus ion goes to zinc 2 plus ion and copper, and they're saying the standard electropotential of this cell is 1.10 volts. First of all, is that spontaneous? Yes, absolutely. Then these are at 1 molar concentrations. Okay, so that's standard state, that's why it's here. But what if I change those concentrations and made them non-standard state? Then I want to know what is the E of the cell. Okay. And that's all they're doing here. This is this. In this particular case, they're putting 2 molar and 0.011 molar. That's all that is. What is this? Okay. So here are my standard state conditions. So this is my E of the cell under standard state conditions. This is the same oxidation reaction, half reaction at the anode. Zinc goes to zinc 2 plus 2 electron. And the reduction half of the reaction at the cathode is copper 2 plus 2 electrons gives me copper. If I connect this to a voltmeter, then that would tell me right away that this is generating 1.10 volts of electropotential. Okay. Now I connect it to non-standard state conditions here. So this is 1 molar of the zinc 2 plus, 1 molar of the copper 2 plus, and I create a 0.01 molar of the zinc 2 plus and a 2 molar, just as indicated before, and I look at my voltmeter and I see it's 1.17 is electropotential. So did I increase the spontaneity or decrease it, first of all? Increased it. And I'm now getting, so therefore I'm getting more energy moving through this external wire going from the anode to the cathode.
Earlier you
But
said,
it could have been the opposite. What, earlier what?
earlier you said that the electrons were moving from the cathode to the anode. This is the other way around?
They're moving from the
Anode to
anode to the cathode. They're moving from the oxidation half to the reduction half
for a voltaic cell.
for voltaic cell. Absolutely, for voltaic. For us, what's the distinction there?
It's spontaneous.
It's spontaneous.
Okay.
Okay, so this is what this is indicating under standard and non-standard state conditions. But what I thought they would get to right away would be this, which makes more sense to me. So here is the delta G under non-standard state conditions by putting it in an equation equal to the standard state conditions in RT log Q.
Okay.
We remember, we recall recently what the delta G is equal to, right, in terms of E potential. So that's what, negative NF
Oh,
E? Okay. So then I could just plug those into each one of those, right? This would be the non-standard E, this would be the standard state E. And there's the negative NF. But if I want to simplify this, I could divide everything by negative NF. And now I have E of the cell under non-standard state conditions, whoops, equals E of the cell under standard state conditions, minus RT over NF log Q. And RT over F was equal, and then changing the natural log to the base 10 was equal to what? 0.0592. So if I do that, I could just convert that into this here minus RTF is now 0.0592 over the number of electrons being transferred times now the log Q. And this is, of course, substituting T at 298. This is 8.315 or 4, and this is 96,400 and whatever that number was, 645 or whatever. Okay, and now I could figure out E of the cell under non-standard conditions. Okay. So what are we going to do next? We're going to solve for it.
where did the 2.303 come from?
So what?
The 2.303?
That's converting between ln and log
Oh.
log.
Yes. Thank you.
What was this called?
Oh,
Cell notation, and remember how to do those? Especially if you don't have a solid. Remember when we walked through that without a solid? We put in a platinum. Make it easier. Okay, so what is this telling us here? Zinc is being oxidized into zinc 2 plus, and silver plus ion is being reduced to silver ion. So we can extract our half reactions from this. This is our oxidation half, this is our reduction half, this is at the anode, this is at the cathode, right? Everybody remember that? Okay, no big deal. What's different about this cell notation than what you've seen in the past?
Concentration?
You have concentrations in there. And are those concentrations at standard state condition?
No.
No. So therefore I need to figure out E under non-standard state condition. Okay. So let's set up the equation. I have zinc, and go into zinc 2 plus and 2E, and I have silver. So these are already given in the proper orientation based on the cell notation, which means that when I look at the reduction potentials, this one has to be flipped from the chart, the first one, because that's the oxidized half reaction. It's given in the reduction half. Those are all reductions. That means whatever is given in this one should be exactly what it is. Whatever is given in here is now flipped, and that just means you switch the signs. Remember, the electropotentials were also called reduction potentials. Okay, I'm going to keep emphasizing that because that's where I see a lot of mistakes on these things. Right? So in the book, in the chart, this would be negative 0.76, which is also how you quickly evaluate. Yes, right. I just want to make that clear that this would be given in the reverse because it's given in this reduction potential. I'm giving it here. If you're giving it like this and it's already set up properly, then you don't have to do anything. You just add them together.
So even though, so for the second half reaction you multiply it out by 2, that doesn't affect like your, you just
Not
said molarity
the
was written-
electropotential.
But molarity was written up there, does that?
Well, but we talked, so it doesn't affect the electropotential.
But it could affect the overall equation.
Absolutely. Because that's given in standard state conditions, so it's always 1. Now it's non-standard state, so now it's going to play a role. Okay. For the overall potential, absolutely. So here I have, this is just going to be the addition of these, right? And that's plus 1.56. So we know what about this? So it definitely will move, and because it's spontaneous. Right. That should be very straightforward. Now, how do I solve the actual E of this thing? Because this is the standard. This under standard, that's under 1 mole conditions. Everything is 1 molar here.
So you could do the different over the n?
Can I use this thing?
Yeah.
So what did I just solve for there?
The E cell.
This. I still need to solve for this, and I still need to solve for Q
Right.
in order to solve for E of the cell.
We know the n.
N is 2.
Now, I look here, I see 2 and 2, those cancel, so n is 2, absolutely. Okay. And, okay, we're looking here, n is 2, what is Q? So which one is a product, which one is a reactant here? And why are only the concentrations of the ions given? Because the others are solids. So they're basically part of the constant, right? So I only care about, this goes all the way back to like an earlier chapter, right? Maybe the second chapter we covered. So all I care about, this is going to be a product, this is going to be a reactant. So reactants over products, so I'm going to get 0.2 molar over 0.002 molar. However, what were the stoichiometric ratios? And this is what I have 1 zinc 2 plus, and I have how many Ag2?
So squared?
2, so I have to square that. So I have to square this on the bottom. Right? Remember, okay.
It's still products over reactants.
It's still products over reactants.
Okay.
This is a product, this is a reactant.
Yes. Got it.
And that's how you read this. That's how you knew this was on the right side, this was on the left side.
Yes.
Right.
So now when I plug it into Q, there we go. No problem? Hopefully I'm breaking this down in an easy way, especially since this is the last lecture you have for Chem 102 before you enter OChem.
Oh.
I want this to be,
Hold on.
I want to simplify this.
I thought it was the silver was the product. I thought that silver was
Because
the
that's not the
product.
chemical equation, that's
This isn't the chemical equation,
So it should be
but you
Z
have to
minus
extract the chemical equation from the cell notation.
Okay.
When did we cover this? This was Tuesdays, okay.
As
Yeah,
well?
this was, yeah, I see, yeah. That's okay. This, so just real quick, I think we have enough time. When you put this together, what side of the reaction in a voltaic cell from this cell notation is this? That's the anode.
All right.
The anode is where the oxidation half reaction occurs.
Yes.
This side is the cathode, where the reduction half of the reaction occurs. So the half reaction, so then the first piece here is what's being oxidized. So this is on the left side of the arrow.
Right.
This line here means that then this is crossing over to what's being, this is the oxidation product of what's being oxidized.
Right.
So this is on the right side, or
Okay.
the product side. Coming over here, this is the reduction half, so the reduction going from plus to 0.
Gotcha.
So this must be on the reactant side, this is on the product side, and that line's indicating that distinction. This double line is just indicating the salt bridge between them.
Yes.
Does that help?
Yeah.
Okay.
Thank you.
And for anybody else? Okay, cool, good, okay. Okay, so then we plug in chug, make sure we know how to operate our calculator properly, and we put in the right log here, right? And I end up with, E of the cell is now 1.42 volts. Okay, which means it's still spontaneous, but it actually, under these conditions, it's not as effective because what was it under standard state conditions? 156, so it went down a little bit, but it's still spontaneous.
And you can kind of correlate it as well because it's, the molarities is actually a little bit less than 1 would have been
Yeah, because this is what we saw in lab.
than the standard.
Decreasing
Okay, so you see the
Yeah.
decrease.
cells.
Yeah,
Awesome.
absolutely. And also you have a different ratio between them, I mean, than the 1-to-1,
Yeah.
right? If they were both 1-to-1 ratio, this would come out the same.
Mm-hmm.
Is the only difference that you can, I guess, have in this cell is different concentration? Because I know you can change temperature, but I don't know
We want to change temperature. You can change the temperature, but what happens in this equation if you do that? Where does the change occur?
Why not T?
The constant.
So it's not really, doesn't apply to the situation.
Well, this constant is only set based on that
298,
temperature.
right.
So you have to just
At
go
25
back.
So
degrees.
you could still potentially keep this. I'd have to think about that a little bit more, but this would clearly change. It wouldn't be 0.0592 anymore,
Right.
right?
You still do the 8.314 times the
What?
change.
No, I was just thinking, you
You
change the
would just do
constant, it's not
you
log.
just do the initial
Right.
one before you
Yeah.
do the constant though. You just do this one.
I
The
can't
one
see.
before.
Yeah. Yeah, the temperature would change. But it actually might change this as well. Depends on how far off you go, because that's set at a particular temperature, which is 25 degrees. So even though this is the adjustment, it's sort of like the adjustment to pressure, volume, and gases, right? Where you use van der Waals equation to make the adjustment under non-standard conditions. Remember that? So you have, it's like V plus or minus something, and the other one is plus or minus something, that add-on from van der Waals, because it's accounting for the difference in potential temperatures, which causes a change in pressure, as opposed to the ideal gas law. It becomes non-ideal, if you recall that. This is kind of similar to that, right? And so, but it might change this as well, and I don't want to comment on it, just that. If it wasn't a big difference, this probably wouldn't change much, and you would change this, but that probably wouldn't change much either overall. But it could have a slight difference, absolutely. It could make a difference. It depends on the system. And it depends, like, especially something that, let's say, the overall cell potential is really close to zero. Then that's going to have a greater effect, because it
Yeah.
could cause something that would naturally be spontaneous to be non-spontaneous, or the opposite.
Right. Okay.
Right. But you would expect, though, as you increase the temperature, what would you expect?
We expect it to, I guess.
You would gain
because
more.
there's a negative.
You would gain more this because you would expect it to move more in its natural progression for a spontaneous.
Okay.
And even for a non-spontaneous, it may be the opposite. You have to think about that.
Okay.
Is that okay? Okay.
You'd have to tell us if it's a non-standard and standard conditions.
Well, in this case, the only thing I'm showing you is that where you don't
Molarity.
have 1 molar of the substances.
Oh.
That is your key, that it's
Everything else is
it's
still,
not
yeah.
standard conditions. That's the only thing I'm introducing here, is the concentration difference. Okay, that brings us to the very last part of this, which is an electrolytic cell. You notice we didn't talk much about this, so I'm not going to probably emphasize this. I may have one multiple choice question or something related to this. But this is where you have, so a voltaic cell, you set it up, the oxidation half of a reaction at the anode and a reduction half of the reaction at the cathode, and you get a spontaneous reaction, right? Or you get something that should move in that direction. An electrolytic cell would be the opposite. I now am trying to force it to go against its spontaneity the way it wants to go, okay? So I have to have a source that drives it to that other direction. And that's just called an electrolytic cell. So electrolysis, I think I brought this up actually. We did the electrolysis in 101 or 65 where we did the decomposition of H2O. Right, we put in a charge and we separated the H2Os into O2 and H2. And clearly that's not spontaneous, because if I didn't put that electrical charge in there, that's not going to happen.
Yeah.
Right? Let me make sure I'm clear on that. And that would be pretty much under most conditions, at least that we would be around. So I'm saying that if I had H2O and I wanted to go to H2 plus O2, and I'll put a 2 here and a 2 here, would you expect that to be spontaneous?
No.
No. If I was maybe going the other way, if I wanted to go this way, that may be spontaneous.
Yes.
But if I want, it might take by the way, I should add this. If I just take some O2s and H2s and throw them together, are they just naturally going to automatically move, even though it's spontaneous in that direction? Like
Might take a
with,
while.
it might take a while. It might take millions of years, but it's still spontaneous. Let's keep that, there's a time frame associated with some of these things, right? I want to put that in context. So I don't know what the rate here is, as we now know what rates are, right? That would be under what kind of study? Kinetic studies, right? We could figure out the rate maybe under different conditions. That's the very first chapter we covered, if you don't recall. But the rate here, I don't know the exact time frame, but if it's spontaneous, it should go this direction. Okay. Non-spontaneous means it's going to go this direction, because that we would never expect just naturally. And in order to make that happen, I have to put in something. I have to put in some charge, or I have to initiate it. So what I'm saying, this would be the direction of what I would do with an electrolytic cell. This is the direction I might want to do with a voltaic cell, even though I'd probably want to make sure that I have a proper rate going and that it's something that's going to generate rather quickly, or at least generate that charge quickly. So here, an electrolytic cell, I'm going to force it the opposite direction it wants to go by adding energy into it. That's all that is. Okay, so let's see. I don't know what one they give us an example of, but since they were talking about electrolysis, it's probably this. Yeah, here we go. Okay, so here they're saying that should be H2O. That's really weird. This should be H2O. It should look like this. Oh, it does? Okay, good. All right. And then what you're doing is you're putting the charge through, and then it's getting into the H2Os, and it's separating them into oxygen and hydrogen. Hydrogen's going to take up a little more space in here. Now, if I have, how can I determine what we did in lab, which one is which, is if I have a little opening here that I can control. So I put a stopcock there that I can close and open at will. And if I open it here, and I put a flame there next to the hydrogen, and I let the hydrogen come out, you hear that popping or that woof sound. Yeah, exactly. And if I did it on this side, what would the flame do? It'd get bigger. If this didn't happen, that means I would just be making the H2O into gas. Then the flame is going to probably get lower. So that's how I'd be able to distinguish what actually happened. Did this actually happen? I could test it that way. And so this would be an example of a non-spontaneous reaction because I had to put something in to make it drive that direction. So looking at that, for all electrochemical cells, you have the oxidation occurs at the anode, the reduction occurs at the cathode. Okay. For voltaic cells, the anode has a negative charge, the cathode has a positive charge. But for electrolytic cells, what's going to happen? The opposite, absolutely. I'm driving the reaction the opposite direction with the power supply moving it that way. So let's take a good, I have it here. So here's an electrolytic cell. So what did we have connected here before for the voltaic cell?
Oh, the meter?
Yeah, voltmeter, right? And that just told us how much energy is being generated going across. But now, right, my direction of the flow was the electrons were going this way.
Mm-hmm.
But now I want them to go the opposite way for whatever reason.
We're still going from the anode to the cathode.
I want to reverse the direction of the flow. You still have the same things in each place.
Then becomes...
If I switched them, then they'd automatically go that flow.
Gotcha.
I have the same things in each place. Remember, do you remember sheet? What was sheet? Standard hydrogen electrode, right? Okay. What happens in that when I mix it with something above it in terms of the chart, the reduction potential chart? It would be more likely to be oxidized, right? Because that's the reduction potential going up. And if I mix it with something below, it's now going to be reduced.
Mm-hmm.
All of these can go both directions.
And that's what happens in lab.
Right?
Mm-hmm.
They all can, because when this is in a regular voltaic system, then the zinc here loses a couple of electrons. It goes into zinc 2+, and the electrons move this way, where they now do what? They attach to the copper 2+, and they form more copper, which builds up on the copper. Remember we talked about that last week when we first introduced this concept. What I'm doing now, that would be the natural spontaneous direction. Now, what I'm saying is I'm going to put a source here that has a positive here and a negative here that drives this way. So I'm now doing what here? I'm losing an electron per copper 2, and I'm forming the copper 2+. I'm forcing the electrons to go in here, and when they go in here, now they're going to attach to the zinc 2+ and form more zinc on top of the zinc, and just reversing the direction of it.
For electric
In
plating.
order to do that, I have to use at least the amount of energy it took to go the other way.
But
And
the-
so it has to be larger than, in this case, 1.1 volt at standard state conditions.
The electroplating is either or is just this one? Doing the electroplating, you were.
Electroplating is just an example of how to, a use of this, right?
Okay.
So you could use this if you wanted to, because, well, why would you use it for electroplating? So you bring up, I think I brought that up last week on Thursday, when we first started this chapter,
Right.
when I introduced the idea of electrolytic cells versus voltaic cells, and I gave an example of metal plating.
Right.
So why would metal plating be used more often with electrolytic cells than, say, with a voltaic cell? Since, I think what you're alluding to is, why not do it the natural progression and make it easier? Why not?
Because naturally that would happen. You need
natural.
some energy to make.
But all I have to do is find a system that allows for that spontaneous reaction. So where the reduction potential's higher for one thing and lower for the other, and I use the lower thing on the
Oh.
oxidation, why would that be? Why would electrolytic cells be more effective in that process than
You can
voltaic
do it
cells?
right away. You can do this faster.
Well, you can
Possibly.
control it more, right? I mean, because you're inputting the voltage.
You can definitely control it more,
Yeah.
but there's a more practical reason for this. Easier, or is it
Fast.
even possible to use a voltaic cell? Where are the things that you want to plate out on? Where are they in that
Like on
reduction
the
potential
chain and
series?
stuff like that. Like,
Yes. Right, so tell me, Jenna, I can tell you
Higher
got it.
up.
Higher up.
Yeah.
And where do I want, what's being plated in a voltaic cell, let's say? What's being plated? So the voltaic cell, this is going this way.
right.
That means that this is going to be the higher reduction.
Mhm.
This is going to be more likely oxidized. But what if my reduction potential, what would I want plated, by the way? So what would I want to put on this? In terms of that, would I want to plate it with magnesium? Do I want a magnesium bracelet?
Yeah.
Yes.
No, I mean, you put a gold.
What do I want? Gold.
Gold, yeah.
I want gold or silver, one of these kinds of things. What are their reduction potentials? Where are white gold, right?
Yeah.
What, platinum? Where are those?
Okay.
They're pretty low.
So they're
Yeah.
more
So
likely
to,
to help.
yes, they're more likely not to be on this end in a spontaneous reaction.
Gotcha.
So then what would I need to do? I would need to reverse that direction and
Yeah.
drive it. I would need this, and that's why that would be more effective and is
Nice.
used in terms of metal plating. Right, that's the best example. There could be other rationale and other things to do. That would be the most profitable,
Mhm.
right? And then usually what drives things that we do in society are, unfortunately, they're a lot driven by profitability. Right, I can give many examples, but then I might be considered too political if I did. Go ahead.
So does that mean if you want to plate something that's lower down on that chart, it would take more voltage? It would take more energy? to
Yeah.
Plate something the lower down?
Well, it depends on what you're mixing it with and that total cell potential with that system.
Sure, but
So
all
that's where
things
you want to
being the same.
optimize what is that system. And part of that though is, what do you have? What are you plating?
Oh, yeah.
Like, you know, am I starting with, maybe I'm starting with something like, well, see, it gets a little interesting because not everything is just an element, right? What if I'm starting with a mixture,
Mhm.
like brass or something, right? That's not just, so then I gotta look at how that's gonna plate out onto something like that. So that becomes a little more complicated. I don't wanna get too off, but this just gives you a sense of what's going on. Okay, so that's what's happening in here. I think I covered everything. I'm just reversing the direction. So then here's a comparison, I guess, between the two. And I'm looking here at a voltaic cell. You have this voltmeter, so you can see how much energy is moving this way. And here you have the source generating it the opposite way. Under standard state conditions, this is 1.10. So therefore, to get it to go this direction, I have to have more than 1.10 volts moving through.
Is there a reason why in the voltaic cell there shows which charge is on it versus the electrolytic cell? There's no charge? Like under the cathode and the anode,
Do the same.
Because the charges are being produced from there.
They're just reversed.
they're just reversed, but they're not written on that one, it's just.
No, well, they're written up here.
Oh, they're written on that, okay.
So I have this here, so this is going to go to a positive down there, and this is going to go from a negative up to that positive, so that's how those are arranged. They're organized. And that's it.
Oh,
Wait, what?
There's another section in the notes.
Oh, we don't.
Then you don't have to worry about it.
Cool.
Okay, so that concludes, which I've liked this class, so, you know, this is one of those things, so if you're taking a class at UCLA, it's like 10 weeks, and you're like, if I like the class, then you're kind of disappointed it's over so quickly, because this is like, you know, 15, 16 weeks. But if you don't like the class, you're like, great, it's done. I didn't have to sit through that any longer. Let me see, I had a question brought up, are we okay with this? I'm gonna turn this off. I had a question on Tuesday. And I think the question was, Jenna, you asked a question, I think. I know it had something to do with studying or something.
Oh, yeah.
Just
Just more specificity about 17.
so I think it's chapter 17 and what to study for on 17, since you already had sort of like an exam on that, right? What do you guys think? So I hear a couple people. What's that?
Our lab exam was pretty rough.
Lab exam?
Yeah, that.
You mean for that section? Is that what you're saying?
With the KSB, yeah.
KSBs and stuff.
It was a lot of. It was deeply conceptual.
It wasn't a lab exam.
Yeah,
It wasn't
it
a
felt more
lecture.
like a lecture exam than a lab exam.
So let me ask. So let's think about this a little bit, right?
Stop recording.